Hello everyone, my name is Zhang. I'm a postdoc researcher from the University of Kent. Today I'm going to present a project done by me and my collaborator Xinrong Wang. The title is Segment Duration and Proportion in Mandarin Singing. If you're wondering what you're seeing here, and if you're thinking, well, this presentation must have been prepared by a teenager who's crazy about anime, that's because it is. Well, I'm really tempted to put in some canned laughter here, but never mind. But the truth is, they are what motivated this research in some sense. What they are is, in fact, virtual singers from Japan and China. They're really famous. Each of them has millions of fans and followers. But what differentiates them from the usual artists is that their singing voices are actually synthesized by computer programs. Now, how I became familiar with this is because when I was working in industry before my current post, I was involved in a project on singing synthesis, or text-to-sing. We won't talk about the technology of singing synthesis today, but to better understand our research questions, let's have a brief look at the general procedures of singing synthesis. There are many ways of synthesizing singing voice nowadays, and every day there are new methods coming out. What we concentrate here is the type of parametric synthesis that are trained with speech data. Yeah, that's the important part, speech data. Here's a simple illustration from a speech-to-sing conversion framework. So this is the condition when you have both the speech data and the singing data. The aim is to use the voice of the speaker who provided the speech data to sing. The model learns the prosodic features from the singing data and the timbre features from the speech data. And then there's a temporal alignment between singing and speech, and then it's synthesized. However, for text to sing, because it's text to sing, there's no singing data involved. Instead, it makes use of the music score and the aligned lyrics, something like this. The syllables are aligned with the notes. But then when it comes to temporal alignment, because there's no singing data, the model wouldn't know the relationship between speech and singing. So it would use the temporal features from the speech data, which then creates problems. Here is a bad case from text to sing. The lyrics are 万事如意. Please pay special attention to the second syllable.
万事如意.
This is the text to sing.
万事如意.
But the original score we put in is actually this. This is human singing with some background music.
万事如意. 万事如意. 万事如意.
I don't know how easy it is for non-native speakers of Mandarin to tell the second syllable in the text-to-sing version is unnatural, but I hope at least you can tell the rhythm is quite different on that syllable even within that version itself. It's also quite different from the human singer's version.
万事如意. 万事如意.
Let's look at it in Pratt. This is the synthesized version, so clearly we can see the proportion of the consonant is quite large, at least larger than the rhyme. This is the human singing. The proportions are different. Maybe half and half, or maybe the consonant is actually smaller. Then let's look at human speaking, because the synthesized singing is based on speaking data. Let's have a look at human speaking. Here it is. In speech, the consonant proportion does look very similar to the text-to-sing version. See, the consonant is quite large. And then to improve the rhythm, to improve the naturalness, we also did some modification by hand. So we manipulated the proportion of the consonant in the syllable. Now it sounds more natural. Let's have a listen. So the text-to-sing original is
万事如意.
the 诗 bit is obviously shorter than the other ones.
万事如意，万事如意，万事如意。
Now it sounds more like the human saying. Let's also compare some numbers. In speaking, the syllable is only 142 milliseconds, while in singing it's nearly double the length. So this is the cause of the problem. Machine learning can only predict based on the data they learn from. Because they never see syllables so long, they can't learn. The way to solve this problem is to figure out the segment proportion and the lengthened syllable in saying and apply the knowledge. As we can see, once the proportion is manipulated and it sounded more like human saying, it sounds more natural. If I have made myself clear by now, then the first research question should be intuitive. When the syllable lengthens, does the segment lengthen proportionally? There's another question we have to ask. What are the factors influencing the way segments lengthen? Phoneme class or skeletal slots? I further picked 4 top categories that had exceptionally bad performance in the output of the text-to-sing model and called them RQ1, RQ2, 2, 4. The first 2 share the same class but different slots. The last 2 have the same slot but belong to different classes. Before I go on, there's another piece of background knowledge we need to know. Mandarin syllable structure. In a nutshell, a Mandarin syllable can be divided into onset and rhyme. This whole thing is the rhyme. The rhyme can be divided into the nucleus and the coda. This coda can either be a nasal or the second half of a diphthong. Not every slot is needed. For instance, the onset can be ignored. Here are some examples. Now we can move on to our data. The corpus we used is an open access corpus. There are 20 songs sang by 20 different amateur singers. The segmentation was first done automatically and then manually corrected. For the analysis, we ran different models, but the simplest linear model had the highest R-square value, so we're only going to present the linear models here. The full results are available in the paper, and in this presentation, we'll only label the slopes because they're the most relevant indicator of the changes. So here, the first question deals with the two syllabic consonants, syllabic approximants. They can only follow these consonants, these 6. The syllable structure is here. Here are the results. We can see from the duration figure that the consonant onset has very low rate of rising, this one, while the syllabic consonant has a very steep slope of lengthening. Accordingly, the proportion of the consonant goes down and the proportion of the approximant goes up. Goes down, goes up. What does this mean? Here's a schematized illustration. So this is a short syllable. When it becomes longer, this one becomes a tad bit longer. And this one becomes a lot longer. The second phenomena is when the approximant, I or U, is the onset. Here are the results. The purple one is the approximant onset. There are a lot more conditions here, so I'm only going to report the numbers for the approximate. As we can see, the proportion goes down, actually, because other things are going up. Now it seems we can answer some of our research questions. It seems whether they're approximate or not does not matter. As long as they're in the onset slot, the duration stays relatively short. Here is a schematized graph again. When it becomes longer, this part of the the onset becomes longer, and the rhyme becomes even longer. I merged RQ3 and RQ4 because they're quite similar in every way. These duration graphs show the nuclear vowel still lengthens the most, regardless of whether it's a part of the VN structure or half of a diphthong. The only difference is the slope of the proportion figure of V1 and V2. It seems quite flat, both lines, which means their proportions hardly change. This could be because diphthongs are a more stable structure than VN rhyme after all. There's a schematized figure again, but as we can see that this is the V, the nuclear V, and this is the coda. It's quite different from the previous ones. So, conclusion. The proportion of the onsets falls substantially when a syllable or a rhyme lengthens. The proportion of a nuclear vowel always rises as the syllable or the rhyme lengthens. The proportion of the coda falls slightly when a syllable or a rhyme lengthens. Another conclusion, skeletal slots encode the duration in Mandarin singing as in speech. Segment classes seem to be a secondary predictor. Not saying it's entirely useless, but not as important as the slots. There are a lot of limitations and there are a lot of possible future studies that can be done. For instance, the corpus is quite small. There are only 20 songs. The analysis is quite simple. And it would be good to investigate other things like beat alignment and what it means for different singing styles and how to relate the result to speech more. Welcome to contact me if you're interested in this project in any way. Or if you have advanced knowledge about music, maybe. If you're interested in singing synthesis, text to sing, speech to sing, and you're a pro in algorithm. If you're really happy to see this research or unhappy to see this research, and I would love to hear your advice. So that's it. Thank you for listening. If you're interested in hearing more about this project, please visit the link at the top of the screen. At the bottom of the screen, there's some of my contact information, and there's also some information about my current project. Welcome to visit our website to have a look what it is. It's a cool project. Thank you. Bye.